right, so let's bring this all together then. So we talked about energy and we talked about work. So work can change the energy. That's what we kind of actually started off with, is we looked at pushing or pulling something, and then the sum of the works, and then you can figure out, you know, kind of how much energy is left to make something go, right? Well, there is this conservation thing that says that energy is neither conserved nor destroyed. So it just goes from one form to the other. The nice thing about energy is that it brings a much more realistic picture of things for you into your heads, because now we're not just talking about things going and not considering how hard it is to make that go. We've talked about forces, but we haven't really talked about it in terms of energy. So what I tell people to do is to start off with making this kind of equations, a group of equations for yourself. So we can kind of mentally talk through what's going on in a system and say that I can always have K initial, so I can be moving. I can always have some potential energy initial. I can have spring potential energy. I have all those things initially. And then in the end, I'm going to have some sort of final kinetic, some sort of potential final, and some sort of spring final. Those are really the three primary forces, or I'm sorry, energies that we're talking about. So for this one, I look at it and I'm like, okay, am I moving? Let's see. The question says, I accelerate a mass from rest. So let's make a little note over here that it's from rest. So V naught equals 0. And V final, do we know that? Nope. Now, I'm told that I apply this force to accelerate it. So that means I have to have a net force. If I have this force applied, that is, let's see, this 6 newtons. And in the picture I gave you, we have this little box like this, and then I have everything labeled on there. That this is the direction of my force applied. There's nothing to worry about as far as my angles go. But I also know I have this force of friction. I know that the mu is this 0.3. And that's it. I know that my displacement is going to be 12 meters. So let's see. I start off from rest. Do I have any kinetic energy? And the answer is no. Do I have any potential energy? The answer is no. Any spring? The answer is no. Any potential energy? Oh gosh, no, no. Oof. So I have this kinetic energy final. What the heck is going on over here then? I just told you energy is conserved. Well, work is what's going on there. So I'm going to have this work applied. And is friction adding energy into? It's going to make it go faster or slow it down. If you answer to yourself that it's going to slow it down, then I would subtract that work of friction. Another way to think about it is that I am going to apply a force over this distance, this 12 meters. That applied force is going to have to overcome the work of friction, and the remainder is going to go into its motion. And we can also accomplish the exact same thing with our angles. So I can see that the FD cosine theta, friction is opposing, this would be my displacement, friction is going that way, so 180 makes that negative. The 1/2 mv squared, well this guy here, this is just energy. We don't have anything other than, let's write those out, mgh, 1/2 mv squared, and 1/2 kx squared. Anywhere in there give you any kind of indication that these things are vector quantities? Nope. These are all scalar quantities. In fact, when I'm done, this energy of joules, those are scalar quantities as well. So let's think about that. So I have this work applied. Do I know what that is? I do. So the work applied is this 6 Newton force times this 12 meters cosine of theta. That force applied is in the direction of the displacement. So that's 0 degrees, so that's positive. Equals the work from friction. Let's see, work from friction. All I know here is that the force due to friction, I'll show you the picture so you're clear. I'm not trying to trick you here. Everything is being applied this way. So let's see, my force, I go up is positive. I have force normal minus the force of gravity equals 0. So force normal equals the force of gravity. So now I'm totally legit here. There's nothing else acting in that direction. So this thing here, I am legit to say force friction equals the force normal times mu, or the force of friction equals mg mu. So let's see. I have the force. It's a 1 kilogram mass. So I know the mass, and I know the coefficient of friction, and I know the distance it's gone. Huh, look at that. So I have mass of 1 kilogram times the distance, 12 meters. Oh, let me just go 9.8, so we're not losing any pieces. 9.8 meters per second squared. So this is getting me into the force of friction piece. Here's my mu of 0.3. So 0.3. Point mu. I don't know what that would be. Okay. So 0.3. So that is my force due to friction. My mg mu. There we go. So now we want the distance that acted over. That's the 12 meters. So that's the work taking energy out of what I'm adding in. This is what I'm adding in. So the next thing then is that plus my 1/2 mv squared. Probably could fit it there. Today you look at me and you're like, but why did we move it over to the other side? It was just to show you we can do it on both sides. So let's go ahead and simplify this. To move these two pieces to the other side, all I did is subtract this over here. I get this 72 from that piece, this 35.28. And that comes out to something I can't add. Oh, okay, now I see what I did. So that comes out to 36.72. And just to remind ourselves, this is joules. This is a Newton a meter. This is a force, that's Newton, and that's a meter. So these two things are legit to subtract from each other. Equals 1/2 mv squared. In this case, mass is just 1. So move the 2 over here. Times 2. So 2 times 36.72 joules divided by my 1 kilogram mass equals v squared. Or take the square root of both sides. Bada bing, bada boom, I get that velocity equals 8.6 meters per second. So I can apply that push, and in the end, I get that box going at 8.6 meters per second, and I've lost some of that work that I put in there to the force of friction resisting it. Cool.